This is day 2 of vectors, and we are tasked with, given a vector in component form, find the vector's magnitude and direction using an angle and standard position. So first we have vector v, and its components are 1, 1. Let's make a drawing of this. It's a coordinate plane. This vector is going to be going like so, because we went to the right one and we went up one. Now if we take this vector v, and we make a right triangle out of this, using a reference angle like we discussed in previous chapter. If we drop a vertical so that the x-axis is always part of the leg of the triangle. If we went to the right one and up one, hopefully you recognize this is a special right triangle. It's a 45, 45, 90. And if you recognize it's a 45, 45, 90, if the leg is 1 and the hypotenuse is square root of 2. So this problem is over before it even begins. The magnitude of vector v is the square root of 2. Reminder, magnitude means length in this context. Sometimes it could mean speed. It could mean lots of things. In this context, it's length. And the direction and standard position, well, what is the angle formed with this vector and the positive x-axis? It's 45 degrees. So we're going to call this theta 45 degrees. If we were to write this in what's called polar form, vector v would have the coordinates. We're going to put the radius length first, followed by theta. So that would be square root of 2, 45 degrees. It's better to use radians, but I'm not going to do that to you at this point. Now let's say that you're looking at this and you're thinking, look, I don't know my special right triangles. I've just never learned it. Can I still do this problem? You can. Let me give you an alternate way to do this if it's not a special right triangle, or if you just don't know your special right triangles. So here's vector v. We know the x and y components are 1 because we're told that they were. So here's angle theta. Here's the radius. Well, using the Pythagorean theorem, x squared plus y squared equals r squared. Notice if you get r by itself, what we're saying here is that the radius is plus or minus the square root of this, and the radius is always positive, so we can just take the positive version of this. So component-wise, keep in mind that this r is actually the magnitude of the vector. So instead of an r, we could call this the magnitude squared. If you square root both sides, then we're saying the magnitude is this. This is a formula that if you want to memorize, you can. The magnitude is always the square root of the x and y components squared and added together. So that's going to be 1 squared plus 1 squared. One plus 1 is 2. So if you didn't know your special right triangles, you would also find that the magnitude of this little fellow is square root of 2. What about the angle? Well, if you don't know your special right triangles, and you wanted to figure out what this angle theta was, you could simply say tangent of theta is the opposite leg over the adjacent leg. So tangent of theta is 1. To get theta by itself, you do tangent inverse to both sides, put this in your calculator, and you're going to get that it's 45 degrees. Now we will have to use this alternate method for some problems if it's not a special right triangle. But I've made every one of today's special right triangles. Let's look at number 2. Supposed to change this, well, not change, it's supposed to find its magnitude, and we're supposed to figure out what the angle is in standard position. Let's draw a picture. This vector goes left 1 and then up 1. So if I go left 1 and up 1, I'm going to be in quadrant 2. we got to figure out what this angle is. We call the reference angle here theta prime. Now if we make a right triangle out of this, we went left one and up one. This is a special right triangle again, with theta prime being 45 degrees. Theta prime is not the answer. The answer is whatever theta is. If theta prime is 45 degrees, from here to here is 180. So I think it stands to reason that theta in this case is going to be 180 minus theta prime. So that's 180 minus 45. That's 135 degrees. If you didn't want to show the work for what I just put in this box, you wouldn't have to. I'm just trying to be thorough in my explanation. And then what's the magnitude? Well, the magnitude of vector u is the length of that hypotenuse, which is square root of 2. This is the same triangle we had in question 1. It's just a different quadrant. So the magnitude, the radius, is always going to be positive. It's square root of 2. So let's write this in polar form. Once again, polar form. We put the length of the radius, the magnitude of our vector, followed by the angle in standard position. So in polar form, this is square root of 2, 135 degrees. Let's check out number 3. We got vector W. It's going to be in quadrant 4. So if you recognize this is a special, we're going to go to the right one and then down square root of 3. So if we go to the right one and down square root of 3, hopefully you recognize it's a 30, 60, 90, with the 60 degrees being the reference angle. Now once again, that 60 degrees is theta prime. We need to know what theta is. In this problem, theta is going to be 360 degrees minus theta prime. That's 360 minus 60. It's going to be 300 degrees. Once again, the work that you're seeing in this rectangle, you don't have to show that if you don't want, but if you need to show it, do so. In this special right triangle, 30, 60, 90, short leg is 1, the hypotenuse is always twice that size. So that means that the magnitude of vector W is 2. So in polar form, put the magnitude first, put the angle in standard position second. This is the magnitude and angle of this vector. These are the same vectors, just written wildly different. Number 3, we have vector S. This is going to be in quadrant 3. So we're going to have to go left square root of 3 and down 1. Square root of 3 is bigger than 1. It looks something like this if we make our right triangle with a reference angle, with a reference triangle. That means we're going to use the x-axis as one of the legs. So we went left square root of 3, down 1. This is a 30, 60, 90 as well. Opposite the smallest side is the 30, opposite the 1, which is theta prime. Theta for this problem is going to be 180 plus theta prime. Theta is going to be 180 plus 30. Theta is going to be 210 degrees. What you see in this box, if you don't want to show that work, you don't have to. What's the radius of this? Well, if opposite 30 is 1, opposite 90 is always twice that. So the magnitude of S is 2. In polar form, we write the magnitude first, we write the angle and standard position second. This and this, same vector. Now, just to remind you once again, what if you don't know your special right triangles? So if we go back up to this picture, and let's say that what we know is that this is negative square root of 3 and this is negative 1. We want to figure out what theta prime is. We could say that tangent of theta prime is y over x. You put this in your calculator. Theta prime is tangent inverse of 1 over the square root of 3. And your calculator is going to give you this is 30 degrees. It's not the answer to the problem, but it's the answer to the angle in this triangle. If you wanted to know what the magnitude was, we could say that the magnitude of S is the square root of the x component squared plus the y component squared. So the x component is negative square root of 3. The y component is negative 1. So that's going to be 3 plus 1, which is the square root of 4, which is 2, which is what we knew all along. Just showing you an alternate way to do this. It's much better if you know your special right triangles, assuming that the information you're given is a special right triangle.